The numbers will ramp up right at the hour, so it's probably good to start, say, 30 seconds late, but don't start too late because then people will come 30 seconds after that, et cetera, et cetera.
Right. I'll give them, well, it's not quite the hour, at least not here.
Yeah, no, it's not quite the hour.
Okay.
Okay, I'm going to mute and turn off my video before my cuckoo clock goes off.
So we're at 2 o'clock. Well, 2 o'clock my time, I guess it's noon on UTC, so it's time to start. Welcome everyone to the plenary session 4B, which is on source models. For those of you who haven't met me, my name is Amanda Weltman, and I'm a research chair at the University of Cape Town in South Africa. And as always, very excited to be a part of these meetings and to hear about everybody's phenomenal progress in such short time frames. So for today's meeting, our first talk is by Sergei Popov, and he will be talking to us live. We are very lucky, the time zones work, on neutron stars as sources of FRBs from the Lorimer burst to SGR 1935.
Okay, can I start?
Perfect. Take it away, Sergei.
So I'm going to give a kind of a brief review how it started and how we finally came to the idea of magnetars as sources of fast radio bursts. So here is a brief scheme. So we start from the bottom left corner, and initially many different ideas have been proposed, and they could be roughly divided into two main parts: neutron stars and all the rest, including all exotics with cosmic strings, primordial black holes, white holes, and so on. However, quite rapidly, mostly because of absence of counterparts in any wavelengths, and because of huge rate of these events, it became clear that exotics doesn't work. So we were left mostly with neutron stars. Of course, I'm simplifying a little bit the picture, but still, neutron stars. And again, we have a kind of dilemma. Either we are facing some known types of transients, or again, there is some exotics, including the confinement, collapse of supermassive neutron stars, axion clouds passing through neutron star magnetospheres, and so on. Discovery of the first repeater in the first place eliminated all catastrophic models, and then also, as we'll see later, allowed to measure distance, host galaxy, and so again eliminated many models. So we were left with known types of transients related to neutron stars, and again we have two main possibilities. Either these are kind of giant pulses, and in this case, we have rotational energy losses, or we have something related to magnetars. And in this case, magnetic energy is the main source of the FRB luminosity. And last year, luckily, finally, people discovered a flare from the known galactic magnetar, SGR 1935. And so the idea that magnetars are sources of FRBs became the idea number one. So at the moment, in terms of origins, in terms of sources of FRBs, again, we have a kind of two possibilities, a kind of dilemma. Either all FRB sources are normal magnetars, which were produced in core collapse supernova, or we need some exotic magnetars formed through different channels. So in the rest of the talk, I'll briefly discuss these topics too. And finishing with this slide, I want to make an important note that actually in a relatively short history of fast radio bursts, many interesting ideas have been discussed, and still many new ideas appear. And of course, most of them are not working for fast radio bursts. Still, it's very interesting to make these theoretical models, discuss these possibilities, because they can be considered as predictions for other types of radio transients. So just a brief mentioning of few old rejected models related to neutron stars. For some period of time, the idea that FRBs are related to coalescence of neutron stars was quite popular. The first paper was published by Tatani in 2013 on this subject. However, of course, now having many repeaters, knowing the rate of FRBs, we are sure that neutron star coalescence cannot be responsible for the main part of FRBs. Roughly the same can be said about collapse of supermassive neutron stars, so-called blitzars, which also was quite popular. The same can be said about deconfinement. It's shown on the right. There were several papers on this subject, and many interesting exotic ideas like axion clouds passing through magnetospheres of neutron stars and producing radio bursts via so-called Primakov process. They were also rejected. The same can be said about the model which was proposed actually long ago to explain gamma ray bursts, like 30 maybe years ago, or even more. The idea that some transients can be related to asteroids falling on the surface of neutron stars. The first main eliminator of theoretical models was the first repeater. Of course, it could work as an eliminator only under the assumption that all FRBs belong to the same class. And mainly I'm speaking using this paradigm. So if we have repeaters, all catastrophic models are rejected. And for the first repeater, it was possible to identify the host galaxy. So again, it's possible to exclude many models, especially taking into account that the galaxy is about 1 gigaparsec from the Earth. And so the luminosity, the isotropic, of course, luminosity of these events could be measured. And again, many models cannot provide necessary energy budget. The first magnetar model was proposed already in 2007. In this short note, we were based on the rate of events, on the time scale of the only burst, the Lorimer burst, absence of counterparts in other energy ranges, and on the energy budget of the event. In this short note, we didn't pretend to make a real model. However, it was possible to rescale some considerations provided by Maxim Lutikov a few years before in connection to normal soft gamma repeaters, and it was possible to show that everything can potentially fit. The idea that magnetars can be sources of FRBs was also mentioned by Thornton and others in their famous paper, but the first detailed model, the prototype model of one main types of present-day magnetar models, was proposed by Yuri Lubarsky in 2014. And in this model, it's necessary to have a nebula relatively far from the surface of a neutron star, and then the magnetic pulse interacting with this nebula produces a shock, magnetized relativistic shock, and this shock can be the source of fast radio burst. Quite a different type of early models was related to giant pulses of radio pulsars, and on the left you see a quite modern picture of statistics of giant pulses of the Crab pulsar, and these pulses can be really strong, but not strong enough to explain FRBs. We know here is on the left characteristic luminosities, isotropic again, underlying luminosities of fast radio bursts. However, it's possible to take the same efficiency, which is the ratio of the luminosity in a giant pulse and rotational energy losses. It's about 1% for crop, and then rescale magnetic field and spin period to explain this ratio of a typical luminosity of a fast radio burst and of a giant pulse of the crop pulsar. And with quite realistic parameters, it can fit potentially. That's why there were many papers, and the paper by Cordes and Wasserman was probably the most detailed on this subject. If this is correct, then rotational energy is the main source of the FRB luminosity. However, this was criticized from different directions in many papers. And here I mentioned just three examples, including a very recent paper related to the FRB in the Galaxy M81. It's quite difficult to use this huge, actually, energy source, rotational energy of a neutron star to produce FRBs. And even if we rescale everything and we have enough energy, then it corresponds to quite a rapid spin down of a neutron star. And this is also a problem because several sources are monitored nearly for 10 years. And if they have very rapid spin down, it could be already visible in terms of spin down, or even in terms of changes in the dispersion measure, if this dispersion measure is due to a remnant around the neutron star. So by different approaches, I would say that rotational energy losses were eliminated as sources of FRB's luminosity. But of course, the main link between FRBs and magnetars was established after simultaneous detection of a radio burst and of high energy burst detected by several satellites. You see them on the top. So it's Konos Wind, Chinese satellite, H6MT InSight, Integral, and Agile. And this is a very strong and important result, and it is discussed in several talks during this conference. And what is important, and what was, I think, a kind of surprise, that the flare was very atypical for this source in X-rays, in high energy band. And you see it on the right. There are many flares, not all are shown, detected from this galactic magnetar, but the one which produced the radio flare is quite different from the rest of them. And so any successful scenario must include this consideration, take it into account. It's necessary to explain why just a tiny fraction, less than 1% of X-ray flares produce visible radio transient. So now main models are related to magnetars. However, even in the next talk, Brian will present quite a different model, also related to jets and shocks, but not necessary to magnetars. Still, main models are related to these type of sources, and there are two directions of studies. The one is presented here. These are models which uses relativistic magnetized shocks. So it's necessary to have medium around a neutron star and then relatively far from the surface of a neutron star, many neutron star radii. The emission is produced due to collision of the pulse emitted by a magnetar flare with the surrounding medium. And here I just took two figures from the paper by Andrei Beloborodov, and this mechanism is quite successful. And in the beginning of his talk, Brian will present arguments in favor of this approach. Another approach is related to magnetospheric events. So there is no necessity to have any specific medium around the neutron star, and everything happens relatively close to the surface. And again, I just took one figure, quite known now. You'll see it many times, I think, during the conference, when if energy is released along open field lines, you can observe successful FRBs. And so now observers try to find arguments in favor of one or another scenario. And recently, I would say this scenario, the magnetospheric one, is winning a little bit. And here is the list of papers which address different aspects of observational data on FRBs to provide arguments in favor of magnetospheric models. One of them, okay, this is just a plot from a nice review by Bing Zhang in Nature, in which this dilemma is discussed in more details. One argument which looks quite interesting is related to polarization. In different bursts of the same source, the polarization angle was changing and even significantly changing during the burst. It's quite easy to obtain such a situation in the magnetospheric scenario, but it's much more difficult to have it in the scenario with external shocks, because they are most probably we are dealing with the same magnetic field structure, and it's quite difficult to change it rapidly on the time scale of milliseconds. Another interesting piece of evidence comes from periodicity, which was also actively discussed during the conference. There are different ideas, binarity or precession. And here I want to make just one comment, but I think it's important because if here we're dealing with binary systems, so the period is related to the orbital period of the binary system, then probably we can exclude for these sources, and they are active repeaters, we can exclude models related with exotic channels because it's quite difficult to make a very close triple system and to explain 16-day period of this source. The rate of fast radio burst is mostly consistent with the magnetar model. So here you see the rate based on FRB observations, and the last orange dot on the left, that's the point related to the galactic magnetar, and inside the area of uncertainty, they can be described by the same distribution, which is quite nice. I'm coming to the end. This is nearly the last slide. So the main problem is now, I think, is related to host galaxies, because the situation is quite controversial. Some papers claim that normal, so core collapse supernova magnetars can explain the whole data on host galaxies. Maybe excluding this source in the globular cluster, but still it can roughly explain types of galaxies, correlations between star formation rate of stellar mass, and so on. Some papers claim that there is necessity to have exotic channels of magnetar formation. And here I come to my last slide. So we have two maybe main problems in the magnetar approach. We have one dilemma related to the mechanism and to the site of emission, either shocks or magnetospheric emission, either correspondingly emission happens far from the surface or near the surface. And another dilemma is related to the origin of these magnetars. Is one channel enough to explain all of them, or we need some exotic ones? So probably for the origin, we have situation more like with these plugs, but for the mechanism, I hope very much that there can be only one. So I stop here. Thank you.
I'll clap on behalf of everyone. It was fantastically well timed with the perfect final slide. I don't see any questions in the Q&A, but Jason has sent one. So his question, Jason, do you want to read it out yourself?
Sure, I can do that. So Sergey, I was at a workshop once with Andrei Grusinov, and he said, you know, radio bursts are cheap. was what he said. And maybe another way of putting this is a lot of these models seem plausible. And we see a lot of FRBs as well. So surely, some of these models might be the ones that dominate the population we see. But is there really any reason why we should be thinking of FRBs as being only one type of thing, one type of mechanism?
Well, of course, it can happen that and this is a population made of diverse sources, and ULXs is the best example, just to make the link with the next talk, because for quite a long time people discussed if ULXs are normal black holes or intermediate mass black holes, but then Matteo Becchetti discovered pulsating ULX, so it was clear that also there are ULXs with neutron stars. So potentially this can happen, but in my opinion, unless we have very clear observational indications that there are different classes of sources, we might try to explain everything with one idea. Otherwise, we really will come to this situation, which actually we don't like using offline conferences. When you come to a different country, to a different hotel, it cannot plug your laptop.
Thanks.
We have time for a last question, if anyone has one. Okay, I think let's thank the speaker again then. And I guess I clap for all. Okay, perfect. So next we have a recording, I'm afraid, because of the time zone issue, from Brian Metzger about accreting X-ray binaries as FRB sources. Here we go.
Okay, it's a pleasure to be here. I'm going to be describing a model for fast radio bursts powered by accreting black hole or neutron star X-ray binaries. This work was led by my student, Naveen Sridhar, who's a graduate student at Columbia. He'll be speaking in a later session on a related but different topic. Oops. Okay, so broadly speaking, you can divide fast radio burst emission models into two categories. There are the near models, where the emission is produced by the inner regions of a neutron star magnetosphere. And then there are the far models where the central engine produces a relativistic outflow that at some much larger radius dissipates its energy in a shock or reconnection event and powers the fast radio burst that way. Although we could argue till we're blue in the face about which of these is the correct model and is consistent with all of the data, I think one way forward is to look at the types of central engines that are producing fast radio bursts. In some sense, the near models are kind of a one-trick pony. They can occur within a neutron star magnetosphere, but not obviously in other environments. By contrast, there could be a variety of different central engines that are producing a relativistic outflow and magnetized shocks. And so the model is in some sense more flexible, not in terms of the physics, but in terms of the types of central engines that could be producing the fast radio bursts. And so if we start seeing similar fast radio bursts from a variety of different sources, that may be suggestive of a far model that does not require a specific neutron star magnetosphere. So I'm going to focus on one particular far model that is very well studied through numerical simulations, and this is the synchrotron maser mechanism that occurs at magnetized shocks. So I have an ultra-relativistic outflow that's colliding with a cold magnetized upstream medium, which could also be material ejected earlier from the central engine. As electrons enter the shock, they gyrate around the magnetic field. This generates a coherent radio burst, which goes ahead of the shock. This is the fast radio burst, the electromagnetic precursor. This is seen robustly in these simulations, which essentially are just solving Maxwell's equations from first principles. And so, combining the fact that this, mechanism has actually been shown to work on a computer, and the fact that magnetized shocks are robust in nature, you can see why I've hitched my wagon to this model. But there's also the fact that it can explain a variety of different fast radio burst properties. The radio frequency is related to the plasma frequency of the upstream medium and the Lorentz factor of the shock. The rate of efficiency is reasonable. The models predict narrow frequency structure of the emission with multiple harmonics that could represent substructure, subbursts. And those bursts are predicted to drift downwards in time because as the shock propagates out, they go into a lower region of lower density, or it slows down, and this causes the structure to drift downwards. You can get high linear polarization. You can get a polarization angle that's either fixed if the upstream has an organized magnetic field, or can flip if it's disorganized. You predict a simultaneous X-ray or gamma ray counterpart. The same shock that's producing the coherent radio emission should also produce incoherent thermal synchrotron radiation. So you should have a near simultaneous X-ray or gamma ray counterpart. And you can produce variability, which is on time scales of that imprinted by the central engine, or even shorter. You may think, well, how can you imprint variability with such a short time scale if the emission is occurring so far away? Well, just to give you a real life example of this, we have gamma ray bursts, which also clearly exhibit sub-millisecond variability in their gamma ray light curves. And we know that the gamma ray emission is not coming from anywhere near the black hole. It's just too dense near the black hole. It must be coming from much larger scales. But nevertheless, because of relativistic effects, you shrink the arrival time of the photons, and you can imprint much shorter timescale variability than you would naively guess from the emission region. So what is the central engine that's producing these shocks and powering the fast radio bursts? Well, we got a hint from the first galactic magnetard to produce the fast radio bursts, SGR 1935. There was 2 bursts of radio waves that were accompanied by 2 hard spikes of X-ray emission on top of a softer envelope of softer X-ray emission. I believe the 2 hard spikes of X-rays and the radio were both produced by the same shock from a plasmoid that was ejected, 2 plasmoids ejected from the magnetar. And in fact, even prior to this discovery, there were predictions for the shock models for the ratio of radio to gamma ray fluence, for the peak energy of the gamma ray photons, and for the spectrum of the gamma ray emission, namely a power law with an exponential decay, which is what you predict for thermal synchrotron emission from fast cooling electrons. And this model can also explain why fast radio bursts and hard X-ray emission are rare from magnetars, because you only see both of them if the plasmoid is shot at you because of the relativistic beaming effect. If it's shot in a different direction, you might see the soft X-rays, but you would see neither an FRB or hard X-ray emission. But is the engine always a magnetar? What gives you pause is the discovery of periodicity in 2 of the most well-studied repeating fast radio bursts, 180916 and 121102, where the bursts arrive within these phase windows every 16 to 160 days. Now, it's not to say there aren't ways in which a magnetar could produce periodic behavior, but I would argue these are in some sense unnatural because we haven't seen this phenomena or confirmed to see this phenomena from any galactic magnetars. And now we also have some fast radio bursts which have been localized away from star-forming regions, or even in globular clusters where there are much older stellar populations. It's not to say you couldn't produce a magnetar in these environments. In fact, I proposed how you could in some papers with Ben Margalit and Ido Berger. But it's not the most natural thing you might jump to immediately. And so our magnetars are red herring. Clearly, they produce some fast radio bursts, but do they produce all or most of them? And what I emphasize is even back in our 2019 paper, the word magnetar did not appear in the title. And in fact, we said many of our main conclusions are independent of the nature of the central engine that's producing the relativistic ejections. Could be a magnetar, but could also be an accreting black hole or neutron stars, I'll talk about in a second, or even a binary neutron star merger, as you'll hear from Naveen. So what I want to focus on is the idea that accreting black hole neutron star systems could also produce flares and shocks and fast radio bursts. And I'm thinking of binaries that are being fed by a companion star and either a black hole or neutron star in the center. And the motivation here is that MHD simulations of accreting systems show that a common occurrence is that a plasmoid will rip off from the inner accretion flow and propagate outwards along the polar funnel defined by the accretion disk wind, this very narrow polar funnel. And so if that plasmoid goes out to large radii and interacts with the pre-existing quiescent jet cavity, you could produce the fast radio bursts at large distances. And that's the idea that we're proposing. So what types of compact objects accreting or their mass transfer rates, accretion rates, would you need to explain the timescales and luminosities of fast radio bursts? Well, here I show the FRB luminosity and timescale. The upshot of this is that there is a minimum accretion rate you need to explain a given fast radio burst luminosity. To explain the timescales, we need relatively low mass compact objects. So supermassive black holes won't work, but stellar mass black holes or neutron stars are okay. And in order to produce the luminosities of fast radio bursts, the most luminous ones at least, we need mass transfer rates which are in excess of the Eddington rate. So the closest analog to the types of binaries we would need to explain the most distant fast radio bursts are ultraluminous X-ray systems, ULX-like systems. And so that's the phenomenology I'm going to focus on going forward. So you could get periodicity in the arrival of the FRBs in this scenario, because you can only see a fast radio burst if you're looking down the fairly narrow polar funnel of the accretion flow, which is particularly narrow if these things are accreting well above the Eddington luminosity. So only if that polar funnel is pointed towards Earth will you see a fast radio burst. But then because of the precession of the polar funnel out of your line of sight due to the lens tearing effect, where the angular momentum of the disk is misaligned with respect to the black hole spin, you could imprint a long time scale variability on the arrival of the fast radio burst. So this is showing you the precession period as a function of orbital period for different ULX systems where people have observed a superorbital period they infer to be precession. And what you see is that the superorbital periods in ULXs actually overlap those of the two repeating fast radio burst sources. And I should also say that you could, in principle, get phase-dependent rotation measure or dispersion measure, because the bursts have to propagate through the accretion disk winds, which have been sort of spiraling around due to this precession process. This model could explain the phasing of the fast radio bursts, the fact that early in the phase we see high frequency bursts and then later we see low frequency bursts. And this is because the jet through which the plasmoids are propagating has angular structure. A plasmoid, even if it's shot along the instantaneous jet axis, will not always interact with the same portion of the quiescent jet because the whole system is precessing. So a plasmoid released early in the active phase will interact with the core of the jet where the density is high and the prediction is high frequency radio emission. Whereas a plasmoid that's ejected later in phase will go out and interact with the lower density sheath of the jet and produce lower frequency radiation. And so you can imprint the angular structure of the MHD jet into the phase structure of the fast radio burst. What about host galaxies? Well, you can compare the star formation rates and masses and metallicities versus galaxy masses of ULX versus fast radio bursts. So the fast radio bursts are shown in orange, the ULXs are shown here in blue. You see some differences. For instance, the fast radio bursts exhibit located in somewhat lower mass galaxies than ULXs, but there are selection effects against detecting ULXs in low mass galaxies. So broadly speaking, I don't think we can distinguish between these two. We couldn't rule out the possibility that all or most fast radio bursts are in the types of environments where in the local universe we see ULXs. One interesting thing is we see ULXs abundantly in interacting galaxies like the antenna, where you had two galaxies that collide together, produce a bunch of star formation. But one of the interesting things is the fast radio bursts, while correlated with the positions of star clusters in these galaxies, are located outside of them. They're not located where the stars are forming. And when I saw this ULX system, it reminded me, and the antenna, it reminded me of Casey Law's 190614, which is a FRB that came from possibly two colliding galaxies at high redshift. It was a very similar environment to the abundance of ULXs we see in the antenna. One prediction of this scenario is the existence of radio, optical, and X-ray counterparts from the bubbles that these ULX binaries blow in their surroundings, these multi-parsec bubbles powered by the super Eddington winds. So here I'm showing you the persistent radio luminosity and optical luminosity of ULX sources, or upper limits in most cases on fast radio burst persistent emissions. And what you see is ULX bubbles do produce X-ray and optical emissions, or radio and optical emissions, but typically the fast radio bursts, at least in the radio, are upper limits. Essentially, they're too far away to detect a ULX bubble. But if we got some closer sources, maybe we could hope to detect these types of systems surrounding some particularly powerful fast radio bursts. One of the interesting predictions or implications of this scenario is that to power some of the fast radio bursts, we need highly super Eddington mass transfer rates. And binary theory tells you that such high transfer rates cannot be stable. We cannot have a star stably transferring mass at thousands of times the Eddington onto a black hole. It should be unstable. The black hole or neutron star should be inspiraling into the envelope slowly of the common envelope. So we may be able to see fast radio bursts originally from these systems, even periodic ones, but their properties should be changing because the binary is evolving towards coalescence. And at some point when the compact object completely plunges into the star, we may see a cessation of fast radio burst emission, but then that would be followed by a transient, maybe an optical X-ray transient produced by this collision event. And so this is an interesting prediction that you may see These most luminous distant sources, if you see them repeat, they may turn off at some point, and then you see a transient that, at least if it's a luminous one, like a fast blue optical transient from this merger event, we may be able to detect it at these distances. So in conclusion, first principles kinetic simulations show that magnetized relativistic shocks generate coherent radio emission with many properties, I would argue, that are consistent with fast radio bursts, including short time scale variability. I would also argue that relativistic flares, plasmoids, and their associated shocks are ubiquitous in nature. They occur in magnetars, they occur in accretion disk jets, they occur possibly in binary neutron star mergers, as you'll hear from Naveen later. I focused on the idea that FRBs could be produced by accreting ULX-like neutron star black hole binaries, motivated by MHD simulations, which show that plasmoid ejection into the evacuated polar funnel of these jets is ubiquitous, and it will collide with the quiescent jet material on larger scales. In order to explain the most luminous fast radio bursts, however, we need accretion rates, accretion powers, which are approaching or exceeding Eddington, similar to known ULX sources. You can get long time scale periodicity in this scenario from precession of the polar funnel in and out of your line of sight. The host galaxies of ULXs are broadly similar to FRBs, although that deserves further study. We may be able to get phase-dependent properties during the active period due to the structure of the MHD jet into which the plasmoids are propagating. We may predict persistent optical radio X-ray counterparts from the ULX bubbles. And in order to explain the most luminous FRBs, we may even need binaries that are undergoing unstable mass transfer towards a common envelope event. And that would be very exciting because FRBs would be probes of common envelope events of black holes and neutron stars at high redshifts. That would be really cool. Those are important for making LIGO black hole binaries. So with that, I will finish. Thank you.
Great. So I will thank Brian, who cannot even hear it, but Naveen will hopefully pass on the thank you. And I think we're very lucky to have him here to answer questions. So I have one question so far from the audience, which is from Dimitri Kangulyan. The very interesting question. So PIC simulations for maser emission. How is it possible to see maser emission, which is a quantum effect, in the PIC simulations, which are classical? I think you need to unmute yourself. Naveen, there you go.
Hi, can you please repeat the question?
Sorry, the question is for the PIC simulations that you do for maser emission, given that the maser emission is a quantum effect, but the simulations are classical, how do you see them from those simulations?
So the big simulations, what they ultimately give out is how the different components of the electric and magnetic fields change in response to the particles' motion to the fields, basically. So you have particles bunching, and so while it's quantized, it's not necessarily it's not that it cannot be captured in simulations, because what we ultimately see is how the electric and magnetic fields respond to the bunching and collapsing of particles in their momentum space. So they are very much easily produced in big simulations. It's just the effect of particles on the fields and vice versa.
Okay, so you still see it. I get it. The next question is from Pranav Lemay. I apologize if I'm pronouncing the names wrong. What assumptions support a slowly rotating magnetar for it to be a possible repeater candidate?
I think I will direct this question to those who are the proponents of precessing magnetar model, because we don't do that. That's not what we show in our work.
Okay, so you want to leave that one.
Yeah.
Okay, how about the following? From Asaf Pe'er. So since relativistic magnetized shocks are very common, example in GRBs and AGNs, wouldn't you expect synchrotron maser in all of these objects?
well, they can operate. So you need transverse magnetized shocks for synchrotron maser to operate, by which I mean that the magnetic field should be transverse to the normal of the shock plane, and there are a few other conditions that the upstream medium need to satisfy in order to see an FRB-like emission. For example, the upstream medium should be cold, and so on and so forth. So only those systems, or only those systems that harbor shocks that satisfy certain necessary conditions, can produce FRBs through synchrotron maser instability. Otherwise, synchrotron maser can indeed happen, but they just won't produce visible FRB-like emission.
Got it. So, okay. Very interesting. Okay, there's a couple more questions. I'm going to just do one more, and then we can push the rest to the coffee session, if that's all right, or to a gather town. So the next question is from Bing Zhang, which is, for Poynting flux dominated jets, sigma starts with a large value and decreases with radius. How do you justify that ULXs and magnetars all produce jets with sigma of roughly 1 at the FRB emission radius?
That's a good point. Not all the ULXs and X-ray binaries do produce the jets, or do produce shocks at a location where magnetization is equal to 1. But this is one of the constraints, in the sense that you need to have not only magnetization a satisfactory value of magnetization, but also that there are many other factors that needs to be satisfied in order for this jet shock to work. For example, there should be the contrast between the power of the flaring jet and the upstream medium should also be very high. So there are many such constraints that need to be satisfied, and certainly not all the ULXs, not all the microquasars that emit jet can produce FRBs. That's certainly a constraint, yes.
Okay. Thank you for that. So I'm going to thank Brian and Naveen for their very engaging talk. And there were quite a few more questions, both in the Q&A and to the panelists directly. If I could just ask you all to take them to Gather Town, I think it'll be a great discussion session. So our next speaker for today is Qiaochu Li, who is speaking to us from Nanjing University, who's speaking to us about periodic activities of repeating fast radio bursts from beryllium X-ray binary systems.
Hello, everyone. My name is Qiaochu Li. I'm a PhD student from Nanjing University of China. I would like to thank the organizers for giving me an opportunity to give this talk. Today, my topic is periodic activities of repeating fast radio bursts from BE X-ray binary systems. This is my outline. First, I will give a brief introduction about periodic repeating FRBs based on observations. Then I will show that periodic activities of repeating FRBs could be produced by BE X-ray binary system from the following 3 aspects. And finally, I will give a summary. Nowadays, the nature of the repeating FRBs, including their central engines, are still uncertain. Last year, a galactic FRB 200428 was discovered from the magnetar SGR J1935, which is associated with an X-ray burst. This indicates that magnetars are at least one origin of FRBs. Recently, there are 2 repeating sources showing periodic activities. FRB 121102 with a possible period about 160 days, and another FRB 180916b with a 16-day periodic activity. The frequency-dependent active window of FRB 180916b is about 6 days. and peaks earlier at higher frequencies. The FRB was found to be about 250 parsecond offset from the brightest region of the nearest young stellar clump in its host galaxy. And this young stellar clump is suggested to be the birthplace of this FRB. It would take million years for FRB 1809-16b to cross the observed distance from this presumed birthplace. This is in tension with scenarios that invoke young magnetas. However, such a large offset may be well consistent with the case of the high-mass X-ray binaries and OB associations. The average offset is about 400 parsecond between them. In the binary star system, Zhang and Gao used the population synthesis method to study in detail the properties of the companion star. And they found the companion star is most likely to be a B-type star in order to explain periodicity of FRB 1809-16b. Here, I'd like to give a brief introduction about the X-ray binary. They can be generally divided into two categories of low-mass and high-mass X-ray binaries according to the lunar mass. The high-mass X-ray binaries are mainly distributed on the galactic plane because the companion stars are young. In high-mass X-ray binaries, the magnetic field of the neutron star will not deviate from its initial magnetic field, obviously, due to the shorter accretion timescales of the neutron star. And the orbital period can be distributed on a wider range from 1 day to 1 year. Notably, there is a subtype of high-mass X-ray binary called B X-ray binary, and the classical B star is a main-sequence B star with a circumstellar disk. The figure on the top right represents a B X-ray binary. They can exhibit type 1 outbursts, which are periodically peaking at or close to the periastron and covering 0.2 to 0.3 of the orbital period. The eccentricity of binary orbits can be 0.1 to 0.9. Their typical orbital period ranges from 10 days to 1 year. It is interesting that the orbital period and the strong magnetic field of the neutron star in the B X-ray binary system are similar to the properties of FRB 1809-16b. This inspired us that a B X-ray binary system might be the source of a repeating FRB with periodic activities. And we applied this model to explain the active window of FRB 1809-16b. The two right figures are schematic illustrations of our model. The dotted ellipse represents the orbit of the neutron star. The gray area represents the disk of the B star. In the disk accretion process, an accretion disk would form around the neutron star when it is in the circumstellar disk of the B star and begin to fade during it is out. The interaction between the neutron star magnetosphere and the accreted material results in the evolution of the spin period and the centrifugal force of the neutron star. This will lead to the change of the stress in the neutron star crust. When the stress of the crust reaches the critical value, a starquake occurs and further triggers FRBs. The waiting time of two starquakes can be estimated by the ratio of the stress relieved during a starquake to the stress buildup rate. When the neutron star is in the B star disk, the interval between starquakes is estimated to be a few days, that is smaller than the active window of FRB 1809-16b. And the waiting time between starquakes is inversely proportional to the strength of the magnetic field, the accretion rate, and there's been angular velocity of the neutron star. When the crust of the neutron star cracks, the magnetic field near the surface would be disturbed and further propagate Earth's alpha waves into the magnetosphere. We can evaluate the energy released by the magnetic energy in the neutron star crust, and it is enough to produce FRBs. When the neutron star is out of the disk of the B star, the accretion will be very weak. The interval between star quakes induced by the radiation of the neutron star becomes much longer than the orbital period, which corresponds to the non-active phase. The lower right figure is the parameter space of period and magnetic field of the neutron star. With the observed burst rates of FRB2021 we can constrain the period and the magnetic field of the neutron star to a limited parameter space. The enclosed area is confined by 3 criteria. That is, the waiting time of star quakes induced by accretion is shorter than 6.1 days, and the waiting time of star quakes induced by radiation is longer than 16.29 days, and there should be interaction between the accreted material and the magnetosphere of the neutron star. Except for the frequency-dependent active window in the figure of the cumulative distribution function of burst rate influence for 1.4 GHz and 150 MHz, we can find more features of FRB2021-16b. First, at 1.4 GHz, the burst rate increases first and then decreases at different phases. Second, FRB2021-16b is about an order of magnitude more active at 150 MHz than at 1.4 GHz at this frequency range. Third, the frequency of the low frequency burst is higher than that of high frequency bursts. As we can see, the average frequency at 1.4 GHz is a few Jansky milliseconds, but at 150 MHz it is a few hundred Jansky milliseconds. In order to get the burst rates at different frequencies as a function of phase, we further generate a sample of FRBs that depend on both frequency and phase, and establish a 3D model to describe the density distribution of the B star disk. We assume that the burst rate during the active window satisfies a Gaussian profile as a function of phase. Furthermore, we assume that the burst rates at different frequencies can be represented by a power law function, and the power law index alpha is negative. The frequency of FRBs at phase phi are assumed to satisfy a normal distribution. Here, mu f nu is the average frequency and sigma f nu is the standard deviation. We assume the average frequency at different frequencies as a power law, with the power law index gamma is negative. And we have assumed a density structure of the B star disk of this form. It can be represented radially as a power law and vertically with an exponential decay. For each burst, it will be affected by the gas in the B star disk. The optical depth of free absorption can be expressed like this. When the neutron star is in the disk of the B star, the optical depth of free absorption along the line of sight would evolve with phase. If the optical depth is larger than 1, the observed flux of the FRB would be significantly reduced. Since the free absorption is frequency dependent, the observed active window of FRBs would be frequency dependent naturally. Then we can estimate the observed fluence of each burst at a certain phase. If it is higher than the threshold of the corresponding telescope, the burst is regarded as observable. The lower right figure is our simulation result of the burst rate as a function of phase. We can see that the peaks of active windows of high frequency and low frequency bursts appear at different phases. Low frequency bursts are appeared later than the high frequency in an orbital circle. Bursts with frequency of 600 MHz have wider periodic active window. Because of the absorption, it had the greatest influence on the burst at 150 MHz, and the burst rate at 600 MHz does not follow the shape of Gaussian model. The above results are consistent with the observation properties of FRB 18096b. We also evaluated the dispersion measure contribution from the B star disk. We found that it is lower than 1 parsecond per cubic centimeter when the neutron star is in the B star disk. And this is also consistent with the observation of FRB 18096b. In summary, we propose that B X-ray binary systems might be the source of repeating FRBs with periodic activities. For the special case of FRB 18096b, our study showed that the periodic activities, burst rate, and the frequency-dependent active window can be well explained. That's all my talk. Thank you for your attention.
Thank you so much. That was really great. I'm going to thank Qiaochu for everybody. She has joined us for the session, so we can ask live questions if anyone has any. So I guess I will take my prerogative as session chair to ask a question in the absence of those in the Q&A. And I'm wondering if there is some kind of distinctive signal that would tell you that this could be the only sort of source.
What kind of source signal?
So if there's if there would be some kind of detection that you would expect, sorry, there's a whole bunch of questions coming in at the same time. That would I think let me read out the questions because there are a whole bunch. Okay, so the first one is from Sander Terveen, which is being searched in the radio, which I think is not far from what I was asking, which is how would you detect exactly these systems and know that it's just these?
Oh, B-X-ray binaries often show emission in X-ray band, so not many systems show radio emission. And radio emission will be absorbed. Maybe this will have a big influence on our radio detection.
So I guess the next question is sort of related, which is from Ben Stappers, which is there any reason why the B X-ray binaries in our galaxy haven't yet given off FRBs? 125963 is well studied during the passage through the periastron. So given that they're supposed to be there, why are we not seeing FRBs? But I guess you answered that in the sense that you don't expect to see them much in the radio. Is that right?
Yes, and in our model, the parameters of B X-ray binaries that can produce FRBs are limited, and this may cause, up to now, B X-ray binaries, these B X-ray binaries, we do not detect any FRBs.
So then, the next question is a good follow-up again. It's almost like coordinated questions from Dmitry Kangulyan, saying, what is the actual mechanism responsible then for the production of the burst, of the radio burst? What's the physics mechanism involved?
In our model, we do not discuss in detail about the mechanism to produce FRBs. We just discuss about the trigger mechanism. And that is because of the accretion from the B star disk, and this triggers the star quake of the neutron star and make the magnetic field of the neutron star disturbed, and the following may produce FRBs.
I see. Okay, hopefully everyone feels their questions are well enough addressed, but if you have further follow-up questions, I encourage you to meet in Gathertown later and to ask them there and to continue the conversation. We're sticking very well to our time. So our next talk is again a recording. Unfortunately, this is definitely a difficult time zone for many, and it's on dynamical formation scenarios for FRB 2021-120E in a globular cluster by Kyle Kremer.
To speak. I'm going to be talking a bit about this recent FRB that was localized to a globular cluster in M81. So there's a lot of reasons this is a very interesting and exciting event. It's a repeater. It's the closest extragalactic FRB that's been observed. And I think probably the most sort of novel aspect is the fact that it was localized to a globular cluster in old stellar population. So in a lot of ways, this event is challenging a lot of our sort of understanding of FRB formation models. So I'm going to talk sort of specifically about some of the sort of ways we expect FRB emitting sources could potentially form in globular clusters based on our sort of current understanding of globular cluster dynamics. So globular clusters are sort of characteristically very old and low metallicity populations. So generally speaking, they're at least 10 billion years old, and at most roughly 10% solar metallicity. In a lot of cases, they're much lower metallicity than this even. So right away, the detection of an FRB in an old population like this immediately poses a big challenge for the sort of standard scenario that's emerged where FRBs are powered by magnetars from core collapse supernova. So in an old globular cluster that's at least 10 billion years old, there are definitely no core collapse supernova happening. So this right away is sort of demanding an alternative formation mechanism for these objects. So typical globular clusters contain of order of 100,000 to roughly 1 million stars. I should also mention that the globular cluster population of M81 is roughly similar to the Milky Way population. There are roughly 150 globular clusters observed in the Milky Way. M81 probably has a bit more than this, more like a few hundred. But the metallicity and age distribution, as far as we can tell for the M81 clusters, is comparable to the Milky Way population. So the Milky Way population is a reasonable proxy for what we expect for the M81 clusters. So clusters have typically 100,000 to 1 million stars, and they're also very compact. So the typical size scale of clusters is of order of parsec. So this immediately implies there are orders of magnitude more dense than the galactic field stellar populations. So this suggests, and it's now very well understood, that as a result of these high densities, globular clusters are very efficient at producing a wide array of stellar sources at much higher rates per unit stellar mass than you would see in galactic field stellar populations. So what I want to do is spend a few minutes sort of painting a sort of broad brush picture of our current understanding of how compact objects are forming in clusters and how compact object populations are evolving in typical clusters, just to sort of set the stage for the ingredients we expect are available to us in old globular clusters to potentially power FRBs. So for a typical cluster, again, with roughly 1 million stars, we expect your initial mass function ranges from roughly 1/10 of a solar mass up to roughly 100 solar masses. So the most massive stars in the cluster, so anything more massive than roughly 20 solar masses. So these mass numbers are all very rough. It obviously depends on the exact metallicity and various stellar evolution details, but just sort of giving rough picture, rough broader overview here. For stars in excess of roughly 20 solar masses, within the first few to tens of millions of years, these stars are going to collapse into black holes. So typically you'll form roughly 1 black hole per 1,000 stars. So for your typical 1 million star cluster, you can expect to form roughly 1,000 stellar mass black holes. So for a low metallicity cluster, these black holes are going to be relatively massive on the stellar mass scale. So typically 30, 20 to 40, roughly 30 on average solar masses. So because these black holes are so much more massive than the average star in the cluster, they're very quickly going to mass aggregate to the center. And this mass aggregation is a natural consequence of dynamical friction, which is operating in any very dense environment like a globular cluster. So this mass aggregation and the formation of this dense subsystem of black holes happens within the first roughly 100 million years of the evolution of the cluster. And then on similar timescales, roughly 30 to 100 million years, the sort of next most massive stars are going to collapse into neutron stars. So because globular clusters are relatively low mass compared to galaxies, their escape velocities are relatively low, 50 kilometers per second, roughly up to 100 kilometers per second, depending on the mass. So we expect that actually the majority of neutron stars that are formed at early times are going to be ejected from their host cluster. And this is a result of the natal kicks that we expect are associated with neutron stars formed in core collapse supernova. So these natal kicks are very are reasonably well constrained by looking at distributions of pulsars in the Milky Way, so the heights of pulsars above the galactic plane. And we expect that, again, because of these high natal kicks, most of the neutron stars that are formed initially are ejected from their host cluster. So we expect that you typically form you'll have roughly a few hundred neutron stars that are actually retained in the cluster and available to participate in the dynamics throughout the subsequent evolution of the cluster. On slightly longer time scales, so starting at roughly 100 million years, 50 to 100 million years, and then going all the way through the entire cluster lifetime, the lowest mass stars, less than roughly 5-6 solar masses, are going to evolve into white dwarfs. So you'll obviously form your most massive white dwarfs first, your oxygen neon white dwarf, which can be as massive as up to roughly 1.4 solar masses, bumping up against the Schoenstatt limit. And then at later times, as the lower mass stars are evolving, you're producing your lower mass carbon oxygen white dwarfs. So for a typical old globular cluster, by the time you evolve to the present day, you can expect in excess of roughly 10 to the 4 white dwarfs. So they're by far the dominant compact object population at late time. So a really important characteristic or aspect of globular cluster dynamics is what's happening in this inner subsystem of black holes. So once these black holes mass aggregate and form this dense subsystem of black holes, they're interacting with one another on very short timescales, and they're constantly kicking each other through these gravitational interactions. And again, because the escape velocity of globular clusters is relatively low, it's very easy for these black holes to actually kick themselves out through these mutual gravitational interactions with each other. So we expect that actually the inevitable outcome in at least a fraction of clusters, depending on the initial density and other features, is that the vast majority of black holes will be ejected by the time you get to their present day ages, so roughly 10, 12 billion years. So for clusters that are eventually through all their black holes by the time they get to their present day ages, in the absence of black holes, the massive white dwarf and the neutron stars, and also the massive main sequence stars that are still left, are going to now be the most massive population. So in this case, these massive compact objects, the white dwarf and neutron stars, are going to mass aggregate to the center, And in these clusters, you're going to form a very dense subsystem dominated by white dwarfs and neutron stars in the massive and sequence stars. So in the Milky Way, roughly 20% of the clusters have reached this configuration, which we call a core collapse cluster. And we expect that these core collapse clusters are sort of the, are very likely the ideal environments for producing fast radio bursts, both because they're the densest, they have the densest, the highest central densities, and also for the reasons I just mentioned, they're the most likely to have the neutron stars and white dwarfs occupying the densest regions of the clusters. And in terms of producing FRBs, especially thinking in lines of sort of the magnetized neutron star formation model, source model, you really want your neutron stars and your white dwarfs to be as dynamically active as possible to produce high dynamical event rates for these objects. So with these things in mind, from a single observed FRB in M81, you can infer a volumetric density from the observation. So we infer a density of roughly 5 million per gigaparsec cubed. And then if you assume that whatever source is powering this FRB in M81 has some characteristic active lifetime for FRB emission of tau, then you can work out the source formation rate for this particular source from simply the volumetric rate divided by this characteristic lifetime tau. So the basic exercise that we pursue in this study that I'm talking about here is we use a set of n-body cluster models, so tuned specifically to Milky Way clusters, but as I said, these are very reasonable proxy for the clusters in M81. And these models take into account all the gravitational dynamics and also the stellar and binary evolution, all of the ingredients that are sort of necessary for these steps I outlined on the previous slide pertaining to compact objects and clusters. And essentially what we do is within these models, we can calculate the formation rate of various mechanisms through which you might potentially form young neutron stars in old clusters. So in this table, I'm outlining some of the possibilities we explore. So just as a few examples, white dwarf mergers, if the total mass is in excess of the Chandrasekhar limit, these could potentially undergo accretion-induced collapse and form a young neutron star. Also white dwarf neutron star mergers, neutron star mergers, and a few other scenarios. So the basic idea is from these models, we can infer the rate per typical cluster. And then based on what we know about the distribution of clusters in the local universe, we can then infer the volumetric rate density we would expect from clusters in the local universe. And then by leveraging this rate density and also the volumetric density for the inferred from the observed event in M81, we can then constrain the active lifetime that would be required for a young neutron star formed through these models to potentially explain the observed FRB event. So just as a sort of example, just to sort of drive things home, for the white dwarf mergers, we're constraining an event rate of roughly 4 to 40 per gigaparsec cube per year. And then with this 50, this 5 times 10 to the 6 per gigaparsec cubed volumetric density from the M81 event, this implies, or this requires, an active lifetime of roughly 10 to the 5 to 10 to the 6 years for the FRB to be, for the source to be an active FRB emitter. In addition to the rates, we can also gain some insight from looking at the energetics inferred from the event. So from the total burst fluence and the on-source time, we can estimate the time average isotropic equivalent luminosity for the M81 FRB. So of course, a key uncertain factor in this is this F sub R, this efficiency factor for how much of the energy is actually going into radio emission. And then we're basically remaining relatively agnostic toward the exact details of how the source is powered, and instead just looking sort of broadly at the energy reservoirs that are available to potentially power the FRB. So as we heard in some of the earlier talks, there is a large reservoir of energy from the magnetic energy of a neutron star, and also there's the rotational energy from the neutron star. In principle, both of these are viable energy sources that could potentially power your FRB. A sort of useful way to sort of frame this picture is to look at things on a PP dot diagram. So this here is showing all of the, for reference, all of the observed galactic radio sources. And then as you often see in these PP dot diagrams, we're showing sort of the characteristic magnetic field values, spin down luminosity, and spin down timescales for various regions of the pp dot parameter space. So the first thing we can sort of layer onto this plot is these colored bands here, which are showing the active lifetimes that would be required for these various formation mechanisms and clusters that could potentially produce young neutron stars. So just again, as an example, looking at this blue band, the white dwarf merger scenario, we see that these again require an active FRB lifetime of 10 to the 5 to 10 to the 6 years for these neutron stars to power an FRB in order to reproduce the inferred event rate. So the next thing we can sort of layer onto this plot is these dashed black curves, which are showing these spin down luminosities that would be required to explain the energetics of the event for a few different values of this F sub r, this efficiency factor for radio emission. And basically the way to read this is assuming a spin down power model for now, the intersection of these dashed black curves with the colored bands is roughly the region of the parameter space where you would want to produce a young neutron star with these properties in order to explain the event. So just as an example, in the white dwarf merger case, this blue colored band, for a relatively low radio emission efficiency, again, it's highly uncertain, but adopting a relatively low value for now, we could infer that you would require a neutron star with spin periods of roughly 10 milliseconds, 10 to 100 milliseconds, and magnetic field values of 10 to the 11 to 10 to the 12 gauss. And it's worth noting that these are consistent with the values predicted from white dwarf merger simulations that are undergoing accretion-induced collapse. So this is again assuming a spin down powered scenario. So assuming a magnetically powered scenario, we can sort of layer on this hatched gray curve in the top right portion of the plot. So assuming a magnetically powered model, you would need a magnetic field strength of roughly 10 to the 14 Gauss. So a higher magnetic field strength would mean a shorter magnetic activity lifetime, which then makes it hard to reproduce the event rate, given the constraints on the formation rate of neutron stars, given these N-body models. And for a lower magnetic field strength, you would need a really efficient radio emission mechanism to produce the event rate. So essentially, a magnetically powered scenario is very viable, assuming you can produce characteristics similar to these that I'm outlining here. It's also worth noting that although maybe not as, well, I should remain agnostic and not judgmental about this statement. There are large numbers of millisecond pulsars that are observed in globular clusters. And from just a pure energetics perspective, there's a large enough energy reservoir available from a spin down luminosity perspective to potentially power an FRB similar to the one observed in M81. In fact, there are actually so many millisecond pulses observed in clusters, and because they have such long spin down timescales, if they are FRB emitters over their entire lifetimes, then it would actually overproduce the event rate based on the M81 event. So millisecond pulsars could be a viable scenario only if they have a relatively small duty cycle for producing FRBs over their total lifetime. So I'll show my conclusion slide. The main punchline is there are a variety of mechanisms that are in principle operating in old globular clusters that could potentially explain this event. There's a variety of ways you could potentially form young neutron stars with properties that are consistent with what are observed. So I'll leave my conclusions up, and if people have questions, I'm happy to answer those. Thanks.
Thank you very much to Kyle. So is he, I can't quite tell if he's available. No. So I think I'm going to defer, I don't see him in the audience. So I'm going to defer the questions to the coffee session or to Gather Town later. So let me introduce the next speaker. Did someone want to speak? I see going on mute. No. Okay. Great. So let me introduce the next talk. We're going to hear from Zhenyin Zhao, about dispersion and rotation measures from the ejecta of compact binary mergers.
Hello, everyone. I'm Zhao. I'm from Nanjing University. Today, I'm going to talk about dispersion and rotation measures from the ejecta of compact binary merge. This is the outline. First is the introduction. I want to talk about connection between the FRBs and the magnetas. Then I will show the DM and IM revolution of the source. We also compare it to the observations. What's more, the offset and event rate is also included. Finally, it is the summary. First is the introduction. FRB2004-28, arranged from the genetic magneta, has been discovered, which has greatly promoted the study of the relationship between the FRB and the activities of magnetas. Therefore, it's important to study the projectors of magnetas. There are made two formation channels of magnetas, instant channel and delay channel. The first one is the instant channel, including core collapse explosions and superluminous supernovae, and the other is the delay channel, including the Byron neutron star merges, Byron white dwarf merges, neutron star white dwarf merge, and the X-ray includes collapse. This talk is trying to answer how to distinguish them. Firstly, the environment. The local environment is different. For different formation channels or magnetas, the mass and energy of the ejecta vary significantly, which plays an important role in the evolution of dispersion and rotation measures. Also, offsets from the galaxy centers and the event rate can also provide us some information about projectors of FRBs. Let's talk about the dispersion and rotation measures. The definitions of dispersion and rotation measures are as follows. dm is the integral of electron density along the line of sight from the source to the observer. Im is the integral of electron density multiplied the parallel magnetic field along the line of sight. For cosmological range FRBs, the observed dm and Im contribute different parts: the Milky Way, the intergalaxy median, the host galaxy, and the local environment of the source. In this talk, we focus on the contribution from the local environment of the source. After core collapse, explosion, and the compact binary merge, the energetic ejecta will sway up the circumstellar medium. During the integration between the ejecta and the surrounding medium, a forward shock with the radiance RB and a reverse shock with the radiance RR are gathered. The forward shock and the reverse shock are spreaded by the shock contact discontinuity with the radiance RC. The space around the young magneta is divided into 5 regions: the wing nebula, the unshocked ejecta, the shocked ejecta, the shocked ISM, and the unshocked ISM. Because the unshocked ISM is not ionized, and there are only 4 of them contribute to the DM source. The unshocked ejecta is not magnetized in general, so only 3 of them contribute to the IM source. To calculate the DM and IM in any time, we should know the electron density, magnetic field, and the radiant evolution for every region. The radiance of the wing nebula expands freely, and the electron and magnetic field is from the energy injection of the magneta. Both DM and IM from this region decay rapidly. Also, the DM from the free expansion unshocked ejecta will also decrease with time. The density profile of the ejecta and the ambient medium is as follows. Where F is the structure function, the inner profile is constant, and the outer profile can be described as the power law with the index, and the ambient medium is also can be described as power law, and the power law index is as if the medium is uniform. For example, the clean environment of the combined merge S equals to 0 if it is in a wind environment. For example, the core collapse of massive stars S equal to 2. The evolution of the shock shear is more complex. When T tends to 0, the behavior of the shock shear obeys a self-similar driven wave solution, and when T tends to infinite, the behavior of the shock shear obeys Shadow-Taylor solution. We use the analytical approximation solution of the evolution of RB, RC, and RR from Tang and Chevalier and Truelove and Mackey, which both obey to which both apply to the similar driven wave pace and Shadow-Taylor pace. In the shocked shear, the matter is compressed and the magnetic field is converted from the shocked energy. Here is the dm and rm from the shocked shear for a merged spiral. It is in the uniform median. The ejecta mass and the ejecta energy are taken as the initial conditions. The initial condition of Byron neutron star merge, Byron white dwarf, and neutron star white dwarf merge are given by numerical simulation in the literature. dm shock and rm shock increase over time in the early similar driven wave pace, and in the Shadow-Taylor pace, dm shock continue to grow slowly, but rm shock decrease. If the density of the ISM is very low, for example, the density of ISM is 0.1, the dm and rm evolution is not obvious. Also, we can get the dm and rm from the shocked shear for a core-collapse spiral. It is in a wind medium. In the same way, here we show the dm and rm evolution for different mass loss rate for the massive star before the supernova. dm shock and rm shock decrease over time, and the increase only occurs when the source age is older than 1,000 years. And we also compare the model to the observations. FRB2011-02, the first repeating FRB, its dm grows about 1% in 7 years. The value of Rm is reported to be very high. The Rm of FRB 1211-02 was being found to decay rapidly, about 34% in 2.6 years. The decrease of Rm seems to be not stable. Maybe the rapid decline at the beginning was due to the Wing Nebula, and the following slow decline was due to the evolution of shock shear. We find only in the case of Byron neutron star merge, the dm from unshocked ejecta is negligible on account of the ejecta expanding at a high velocity. For other cases, the dm is mainly controlled by the unshocked ejecta, and it is impossible to reproduce the detect increasing dm. Here are our fitting results. Time starts from the birth of the magneta. Here we said the ejecta mass is 0.01 solar mass. The energy is 1 times 10 to the power of 51 erg, and the velocity of the Wing Nebula is 3 times 10 to the power of 8 centimeter per second. dm other is the sum of all contributions except the source, which is assumed to be unchanged. We find the source age is about 10 years, and when it was first detected in 2012, and the ambient density is about 3 cubic centimeter. Then I want to talk about the offset. Here are the properties of FRB host galaxies. Some of the localized FRBs, whether it repeat or not, have been found to have large offset from the galaxy centers. Large offset indicates that they may originate from the Baryon neutron star or Baryon neutron star white dwarf merge, because neutron stars receive native kicks as a result of asymmetric supernova explosions. And the next section is the event rate. The event rate of FRB has been reported to be very high. It's about 30 to 60,000 per cubic gigapascal per year. According to GW 170917, the event rate of Baryon neutron star merge is estimated as 1,540 per cubic gigapascal per year. To estimate the merge rate of neutron star white dwarf and Baryon white dwarf, we use the BSE code to carry out a population synthesis. We created a catalog of 1 million Baryon systems in which the initial system patterns satisfy the following distributions, where M1 is the mass of the primary star, Q is the mass ratio of the two stars, epsilon is the eccentricity, and the P is the orbital periods. The metallicity is 0.02, and the maximum evolution time is 15,000 million years. The constant Baryon fraction is used in our simulation, and it is assumed to be 75%. The merge rate is a convolution of the star formation rate history rho z and the probability density function of delay time. The cosmic star formation rate rho z is this, and finally we get the merge rate of neutron star white dwarf is about 319 per cubic gigapascal per year, and that of Baryon white dwarf merge is about 20,000 per cubic gigapascal per year. The large offset of some FRBs are consistent with the Baryon neutron star merge and neutron star white dwarf merge channel, but merge rate is much smaller than FRBs. The event rate of Baryon white dwarf merge is close to FRBs, but it cannot explain the large offset. FRB 2004-28 is associated with the genetic magnetar host in the supernova remnant. It implicates that at least some magnetar was born in the supernova can produce FRBs. From the above discussion, we can get that there are varying projectors of FRBs. Finally, it is the summary. For compact Baryon merges, both DM shock and arm shock increase over time in the early self-similar driven wave pace, and in the shadow of Tyler pace, the DM shock continues to grow slowly, but arm shock decrease. The DM from the unshocked ejecta of Baryon neutron star merge is negligible, and the case of Baryon neutron star merge can explain the DM increase and RM decrease of FRB 121102. And from the discussion of the offset and event rate, we know that projectors of FRB may not be unique. Thanks for your patience. Hello, everyone.
Thank you very much for that. I'll applaud on behalf of everyone. We have a question from Sergei Popov. When you quote white dwarf merger rates, of a few times 10 to the 4 gigaparsec per gigaparsec to the -3 years. I can't quite read what that says. Do you mean all white dwarf pairs, or just those with total mass above the Chandrasekhar limit?
Oh, okay. It means all the white dwarf pairs.
Does that answer your question, Sergey? He's replying saying, is it relevant? You're a panelist, you can unmute yourself and reply directly.
But as we are discussing neutron star formation after the merger, is it relevant to quote the total white dwarf merger rate? Because in most of the cases, there'll be just a massive white dwarf, because average masses of white dwarfs are about 0.6 solar masses. So more than 1/2 of mergers do not produce neutron stars, and many of them produce supernova 1A, even if they are supercritical. Thank you.
Okay, we don't think it's in detail. We just think all the white dwarf pairings don't consider the fate of the after the merge. Maybe its rate will be lower. Thanks.
Okay, thank you.
Any further questions? Okay, I will thank the speaker again on behalf of everyone. And we move on, I believe, to the final talk of the session, which is binary comb models for FRB2011-02 by Tomoki Wada. And again, we have a recording, as I guess we are the second version of the session, and the time zones are very difficult.
Take it away.
Thank you. Hello everyone, I'm Tomoki Wada at YITP. At first, I thank for organizers to giving me this opportunity to talk about our work with Professor Yukawa and Professor Zhang. Today, I'd like to talk about the binary comb models for FRB 121102. While many people may know about FRB 121102, I'd like to overview some properties of the burst. FRB 121102 is the first repeating FRB. The burst rate is shown in this top figure. This is very nice observational result of burst in China. Its burst rate energy peak is at 5 times 10 to 37th L. This is here, top of this Gaussian-like shape. And the fluctuation of the fluctuation of the dispersion measure is about 6 per centimeter cubic times per sec. This is as shown in this figure. And FRB 121102 shows very high rotation measure, about 10 to 5th power radian per meter squared. This is also a special property of FRB 121102. And its host galaxy is a dwarf galaxy at z equals 0.2, and its mass is about 10 to 8th power solar mass. The very interesting point of FRB 121102 is the persistent radio counterpart. Its luminosity is about 10 to the 39th power ergs per second in radio band. It is plotted in this about 10 gigahertz region, and its size is smaller than 0.7 per sec, and it is off center. And also FRB 121102 shows periodic activity. Its period is about 160 days. The yellow region in the right top panel is the active window. FRBs are observable only in these yellow regions, as shown in the bottom figure. In one period, FRBs are observable only in this active window. This active window corresponds to this yellow region in the upper figure. And in the active window is about 50% or more. At first, graduate at all 2020, showed that the active window is about 47%. However, in later paper, Cruzas et al. 2020 showed that the active window is more than 50%. Some models are proposed to explain the periodicity of FRBs. There are mainly two kinds of models. One is the binary model here. The periodicity is realized by the orbital period of the binary. To make the active window, we need some models in which FRBs are emitted in some part of orbital period. It is in this region. The other model is the precession model. And the period of the first radio burst is realized by the precession of the pulsar. In this model, the FRBs are beamed, and we can observe the FRB when this beam is open to us. Other models are also proposed. For example, the spin of the neutron star is the period of the FRBs. In these models, I'd like to show that the binary cone model can explain the period of FRB 121102. This model is proposed by Ioka and Zhang 121102. This model is proposed. This model is proposed by Ioka and Zhang 2020 to explain the periodicity of the first periodic first radio burst. Using and developing this model, I'd like to show that the period of FRB 121102 is also realized. In the model, one of the binary emit FRBs, that is this pulsar. We call this FRB emitting source FRB pulsar. The wind of the companion, this wind, can scatter or absorb FRBs from the FRB pulsar. In the optically thick wind, this green region, the wind of the FRB pulsar creates a funnel, and the FRBs through the funnel are observed. This is the funnel, and through this funnel, FRBs can be observable to the observer. Then the observed periodicity is realized, because in this region, FRBs are observable, but in these regions, FRBs are not observable. I'd like to I'd like to use this model to explain the period of FRB 121102. At first step, to apply this model to FRB 121102, I'd like to evaluate the optical depths of the binary for FRB 121102. The observed periods determine the symmetry axis of the binary, and then the number density of the companion window is determined, like here. Taking polar coordinates shown as right figure, we can evaluate the optical depths of the system. Basically, the binary is transparent to Thomson scattering, which is not shown here. However, free absorption and induced Compton scattering of the companion wind makes the binary optically thick. Thus, the wind from the companion, this blue region, basically makes the system optically thick. Then, how the period is realized in optically thick binary. There are three solutions we found. One solution is the funnel created by the FRB pulsar. This is the original idea of the binary cone model. If the FRB pulsar wind creates a funnel in the companion wind, the bursts through the funnel are observable. In active phase, in this red region, in active phase, the line of sight is in the funnel, like this line. Then the FRBs are observable because they pass through the funnel. And in its inactive phase, this blue region, the line of sight is out of the funnel like this, and FRBs are blocked by the companion wind. In this mode, there are three conditions. First, wind must be optically thick for FRBs to absorb or scatter the FRBs in its inactive phase. Second, the half opening angle of the funnel, this angle, Theta C must be such that the duty cycle can be explained. Third, this funnel must extend radially for FRBs not to be blocked by the companion wind in its active wind. This is one solution, and we call it funnel mode. And other solution is the change of the optical depth in the orbital phase. The FRB pulsar is orbiting the companion, and thus the optical depth along the line of sight changes in time. For a given eccentricity and observed active window, we can determine the orbital phase where FRBs should be observable. The phase is red in this figure. If the binary is optically thin in this red curve and optically thick in blue curve, then the observed periodicity is realized. The observed active window is explained if binary becomes optically thin in its active phase and optically thick in its inactive phase. We call this solution tau crossing mode. The other solution is the strong FRB pulsar wind. If the FRB pulsar wind is so strong that the companion wind, these blue regions, is pushed back, as shown in this right figure, the FRBs are basically observable because wind basically do not block the FRBs like these arrows and these arrows. However, when the companion is in front of the FRB pulsar, if the observer is here, we could not observe FRBs because FRBs are blocked by the companion and companion wind. This mode is similar to the eclipse. To realize this mode, the FRB pulsar wind is strong enough as shown in the bottom of this slide, like this as this equation. We call this mode inverse funnel mode. So far, I showed 3 models to make FRBs observable in the active window. Later, I will use this model and determine the host binary of FRB2021. The question is what binary is possible as the source of FRB2021? We consciously kind of companion stars, massive star and intermediate mass black hole and supermassive black holes. The adapted parameters are shown as here, mass and wind velocity. Fixing mass and wind velocity, we put constraints on the FRB pulsar's wind luminosity and companion mass loss rate and the eccentricity of the binary. The used parameter about paths are here. First, I'd like to show the supermassive black hole companion case. Here we set the mass 10 to 5th solar mass and the wind velocity 0.1 c. The vertical axis represents the wind luminosity of the FRB pulsar, and the horizontal axis is the mass loss rate of the disk wind of the supermassive black hole. In the funnel mode and tau crossing mode, the colored region without the dashed line is allowed. These regions. And the color contour shows the eccentricity. The region above the magenta line is also allowed in the inverse funnel mode. The dashed line is excluded because the change in the dispersion measure is higher than the observed value. And above this green line or right of this green line is in this region, the persistent radio counterpart is explained by the nebula or companion wind. I'd like to show some detail of this figure. First, this small region is allowed by the funnel mode, and this region are allowed by the tau crossing mode, and this region is allowed by the inverse funnel mode. So, to summarize, the colored region without dashed line and above the magenta line in our binary is allowed in our binary model. In this case, the persistent radio emission is energized by the AGN jet, nebula emission, or disk wind. If energized by the disk wind, the radio emissivity must be higher than 1 to -4. Also, high rotation measure may be due to the high magnetic field near the supermassive black hole, like magnetars in our galaxies. Next, I'd like to show the massive star companion case. We set mass of the companion as 10 solar mass, If we set the wind velocity as 0.01 c, the persistent radio emission is not as luminous as that of FRB201102 in this region, in the funnel mode or type crossing mode, these colored regions. And only inverse funnel mode is possible as the source of FRB201102 above this magenta line and this green dotted line. In this case, the persistent radio emission may be energized by the nebula emission.
2 minutes to go.
2 minutes, thank you. Here is the intermediate mass companion case. We set the mass as 10 to the third solar mass and the wind velocity as 0.1 c. The figure shows the intermediate mass black hole can be a source of FRB201102 in this colored, not dashed region and above this magenta line. I note that the high velocity wind, for example, in this case, 0.1 c, is essential for parameter for constraining parameters. If we set high wind velocities of the companion, the funnel gets longer and the change in the dispersion measure gets smaller and kinetic luminosity gets higher. Thus, it becomes easy to be the source of FRB201102. This is the short summary of my talk. And at last, I'd like to introduce some scenario that can explain the frequency dependence of the active window. This feature is detected in FRB180916. Okay, I don't describe details, but I'd like to overview these models. One possibility is the frequency dependence of the active window. One possibility is that the frequency dependence of the active window is due to the companion of the different sensitivity of the different telescope, this yellow line, and the absorption in low frequency. And another possibility is that the frequency dependence of the active window is due to the intrinsic emission mechanism. If the binary of FRB180916, 16 has some eccentricity, the emission may vary with the orbital phase due to the separation or the wind velocity of the companion changes, and the active window may change depending on the frequency. Okay, this is summary of my talk. Thank you very much for your attention.
That's great. I'm going to thank the speaker for everybody. From what I can tell, he's not actually available in the session. So unfortunately, we won't be able to have a live Q&A, though I do see some questions appearing. I recommend perhaps that you follow up either in the GatherTown discussions later or on Slack. The Slack channel is live and ready for discussions. So with that, I think the session is over. Thank you to all the speakers and everybody for attending and listening to the talks. The next session starts in 2 hours, whatever your time zone is. Thank you very much.